now we're making a sort of transition in our course. We're moving from the study of algebras and general things to the study of more specific things. Okay? So the theories that we want to study are supersymmetric Yang-Mills theories. The first theories we want to study are supersymmetric Yang-Mills theories in 4 dimensions. And we will largely be following this review by Seiberg and Trinegator for the study of supersymmetric Yang-Mills theories with n equals 1 supersymmetry. Okay, but before we start looking at these theories, I need to start telling you a little bit about. I need to tell you a little bit about superspace and the the mechanics of writing down supersymmetric theories in 4 dimensions. Okay, so you remember that in the first part of our course, when we studied supersymmetric quantum mechanics, we invented a space called superspace. So that functions of this space, so that theories that were written down in superfield language would automatically be supersymmetrically invariant. Okay. Now there is an analogous procedure in every dimension, and what we're going to do is to go through the procedure for that in 4 dimensions, just so that you know what, so that we can write down the theories easily. Okay. For this part of the lecture, I'm following this book by West and Bagger called Supersymmetry and Superfield. Okay, we're going to look at okay. So consider 4 dimensions. We're in 4-dimensional space, and in order to make a superspace, you remember that we had in the basic version of supersymmetry, we had 1 theta and 1 theta. Okay, that's because effectively we had 1 q and 1 q. Roughly speaking, q was del by del theta, but then there was some there was an additional theta del by del t. Okay, so we need to have as many thetas as we have supersymmetry, so that we have as many del by del thetas as we have supersymmetry. Right? So what we want to do is to start studying n equals 1 theories in 4 dimensions. Okay, n equals 1 theories in 4 dimensions are theory with whose supercharges are q bar, the q alpha and q bar alpha, where this alpha index is a spin under the first SU2. Okay, and the first whatever influence in space SL2R. Okay, and the beta dot index is the spin under the second component of appropriate real version, or appropriate complex version of C. Okay, this we sort of used to, right? This is a chiral spinner, and this is an anti-chiral spinner. Under SO4 or the appropriate real version. Okay. Now, because we're looking at n equals 1 supersymmetry, we have no flavor indices. We have no R symmetry indices. Right? That's what n equals 1 means. There's only one version of the supercharge. So we don't have an extra R symmetry index. Now, you remember that the R symmetry in 4 dimensions was UN, where n was the number of supersymmetries. In this case, the R symmetry will be U1. And because n is equal to 1. Okay, so there's still a possibility, even though we're looking at minimal, the minimal content, there's still a possibility of R symmetry. It's just that this R symmetry will be this abelian. As we will see as we go along, it will be a symmetry under which Q picks up is phased in one way and Q bar is phased in the other. Okay, so now I want to invent a superspace. Okay. I want to invent a superspace that will have. I want to invent a superspace that will have that will allow me to express these this Q and Q bar. Okay, so what I do is to have a theta alpha and a theta bar alpha. That sounds reasonable, right? Because as many thetas as we have Qs. Okay. Then we define the following vectors. Q alpha equals del by del theta alpha minus I sigma alpha alpha dot mu del mu. And theta bar alpha and del mu. Okay. This you should remind yourself, this should remind you of in our quantum mechanics. We had our Q was, I can't remember the sign, but it was like del by del theta plus del T minus del T. Theta bar, del T. Okay. And so you see, you have the analog of the theta bar here. You have the analog of the del T here. So in quantum mechanics, del T was del T because it was only one dimension extend here. Now we've got del mu. Okay, we want to make the whole thing Lorentz invariant. So we multiply by the sigma matrices. Okay, now these sigma matrices are matrices that couple two spinors to make it a vector. Right? So these sigma matrices from that point of view have an alpha dot and a mu index. Right? It's an invariant tensor under SO3,1. It's invariant when mu transforms like a vector, alpha transforms like a chiral spinor, and alpha dot transforms like an anti-chiral. This is clear, right? So, this sigma mu is the object that allows us to, is the object that expresses the fact that a vector is a product of two spins, product of a chiral spinor and anti-chiral spinor. And it is the object that expresses that fact and allows us to convert from one to the other. Okay, so this sigma multiplied by the derivative converts it into a bispinor, and then we dot with a theta alpha alpha dot, and that gives us what's left is just an alpha. Okay. Now, there are various conventions as to for raising and lowering indices for these spinor indices. Okay, and these conventions are basically that they're raised and lowered with sigma 2 or epsilon. And I'll come to those conventions as we go. Okay. So this is Q, and then there is Q bar alpha. Okay. So Q bar alpha is the following. It's equal to minus del by del theta bar alpha dot.
So the Q bar alpha dot is
what? Thank you. Q bar alpha dot is minus del by del theta alpha dot plus I theta alpha sigma alpha alpha dot time mu times theta. I think when we wrote down our sigma bars, we may have done it our del bars. In the quantum mechanics, we may have put a plus here and a minus here. Doesn't matter. Some convention issues. Okay. Now, the point about this is that this representation obeys the supersymmetry. Okay. So let us start getting used to these manipulations. In order to start getting used to these manipulations, let's take that. Okay. So what was the supersymmetry algebra? The supersymmetry algebra was that Q alpha, Q bar alpha dot. Okay. What? Beta dot, fine. Beta dot is equal to basically P mu.
sigma.
So we need sigma mu alpha dot beta dot del mu with some number here. This is the supersymmetry algebra we expect. Yes. Okay. So we want to check that these differential operators obey that supersymmetry. There'll be I or something. Yes, very possibly. Yeah. Let's see what we get.
Isn't it epsilon alpha dot is an invariant tensor in this space?
Epsilon alpha dot, but we don't want an invariant tensor. We want momentum.
Yes, it should be always proportional to the momentum.
To the momentum. The epsilon would double that. Firstly, there's no epsilon. There would be like a.
I'm saying mixed index. I'm saying there can be more tensor structure possible, but you want momentum.
We want momentum. There's an extra term possible if we have if we have an arsenal. Yes, right now let's forget that. We just want the term of momentum. There's only one thing we could have written down, right? Yes. We want momentum alpha dot. Alpha beta dot. Okay, excellent. So, well, delta alpha beta dot doesn't work. It's alpha and beta dot are in different ways. But you're right that they these are different SUs, right? So this alpha transforms under SU2 left. That alpha transforms under SU2 right. Okay, so delta alpha beta dot is not going to work.
Epsilon was the thing, I think, equivalent of this delta.
But it's same kind of.
No, same kind of analysis. Yeah. What? Yeah. What would you're asking? What works for the arsenal?
I think we saw this one depending on Z is symmetric or anti-symmetric.
Yes.
You will get a thing which will multiply, whether you get delta or
Yeah. We saw that basically in the general language, when we had Q abstractly, where Q zeta prime, we had a C zeta prime, right? Thanks, Z. Now the C could have, sorry?
Could have been any symmetric. So delta could be
Yeah. Yeah. You know what's going to happen here is that this relation will not be changed. Yeah. What will be changed is that there will be like a Q alpha, Q beta. This will have a Z epsilon alpha.
Yes. Yes.
That's the only kind of thing that's possible. Yes. You can't have any varying tensor between one SU2 and another. Right? But this is the reason I didn't want to. Okay, get into that. Okay, forget about the arsenal. Okay, excellent. So let's check that Q with Q bar as what we expect. Okay, so let's follow Schumann's lead and call this beta. And this is beta. Okay, so what we want to do is to compute the anti-commutator del by del theta alpha minus I sigma alpha dot mu del theta alpha dot del mu with the anti-commutator of minus del by del theta bar. We call this beta. Beta. Sorry, this was alpha and this was beta. Thank you. Okay. So we want this with minus del by del theta bar beta dot plus I theta alpha sigma alpha beta dot mu del mu. Okay. Now the first thing we want to do is to see which terms here can have non-trivial anti. You see, this is theta, this is theta bar. They have nothing to do with each other, so they have no non-trivial alpha. Okay? And similarly, this is a theta bar, and this is a theta. So these two terms have nothing, they have nothing to do with each other. They are non-trivial. Just multiplication by different algebraic expressions. The only non-trivial anti-commutators are going to come with this, and this with this. That's clear? Okay. So let's see. And the non-trivial anti-commutator of this with this comes because this guy acts on this guy. Okay. So this we should have called a mu, because it's a dummy index, not a mu, gamma, because it's a dummy index. But when this alpha hits this gamma, alpha becomes gamma. Okay, so the term from here becomes I sigma alpha beta dot mu del mu. Okay, what about the term from here? What about the term when this guy hits this guy? There are two minus signs. Okay, yeah, there are two minus signs, and we just get exactly the same. Remember, there's no additional minus sign for which order because it's an anti-commutator. Okay, so we get 2i. So it should have been 2i. 2h. Lovely. And the i is what I want. Okay. So you see that we have this nice result. That these expressions implement the supersymmetry algebra, just like we did in quantum mechanics. Okay. Now, suppose we continue. Okay. The next thing we had when making interesting sort of actions. The next thing we had when making interesting sort of actions with quantum mechanics is this operator D. You remember it? Yes. Okay. It was very much like the supersymmetry operator, except it had an opposite. Yes. So let's check that. So once again, here we make similar definitions. D alpha is equal to del by del theta alpha plus plus I sigma alpha beta dot theta bar beta dot and del mu. Whereas d bar beta dot is equal to minus del by del theta bar beta dot plus I plus here. This is a plus now. No, minus, both are minus. Minus and minus. Minus I theta alpha sigma alpha beta dot mu and del. Yeah, alpha and s mu. Okay. Now, if you remember, when we were studying quantum mechanics, the point of the definition of the D operator was that it commuted with both supersymmetry. Okay, that D alpha commutes with Q alpha is obvious because it has del by del theta and there's theta. There's no term that could possibly not commute. Okay. The only thing that is not obvious is that D alpha commutes with Q alpha with Q bar beta dot. And the way it's going to happen is exactly the way it happened last time. Of these two terms, one will come with a plus and the other comes with a minus. Exactly like in quantum mechanics, the plus and the minus cancel each other. And the two terms cancel out. You can see the plus and the minus becoming, right? Because one of these has a plus here. So if I do this with this term will come with a plus, whereas this term will come with a, whereas this term will come with a minus. and they will cancel each other out. It's the same algebra apart from sine field. Okay. So once again, we have just like we had in the quantum mechanical case, we have the formula that d alpha q bar beta dot is equal to 0. And similar relations for
Or any d comma q is 0.
any d comma q is 0. So d bar alpha q beta, alpha dot q beta is also 0, and the other two of course always. D alpha q alpha is equal to 0, d bar alpha dot q bar beta dot is also 0. Okay, all good? Fine. Now that I've got used to the blackboards and 8066, this feels like this is no place. Okay, excellent. Now, if you remember, what we did when we were studying supersymmetric quantum mechanics was we used these D operators to put supersymmetrically invariant constraints on super. So first, what is a superfield? So superfield, if I take a general superfield phi, it's just some general function of x mu, theta, and theta bar. Simple enough. How many components does a general superfield like this have? 4. No.
Sorry.
How many components are expanded in terms of bosonic fields?
Sorry, you will expand in theta and theta bar. Right?
Yeah, 16. Because there are 2 thetas and 2 theta bars.
Sorry. Yes.
So
that count.
Yes. Each theta could be there or not. Each theta bar could be there or not. So we have 2 into 2 into 2 into 2 possibilities. So 16. Okay. So the most general chiral superfield has 16 components. We have very similar counting when we looked at the n equals 2 theory with quantum mechanics. We have 2 thetas, 2 theta bars. We talked about how we could have the most general superfield having 16 components. Okay, and as in that case, we decided that was a pain. 16 is a very large number of fields. Maybe we wanted to deal one day with some very complicated theories like n equals 4 angles, which will have a order 16 fields. But at the moment, we're just beginning. We want to deal with minimal theories, small number of fields. So we wanted to ask how we could impose a constraint on our field content, but a constraint that commutes with supersymmetry action, so that will continue to allow us to make supersymmetric actions. And just as we did with the quantum mechanics, we're going to impose a condition d bar alpha dot on phi. One interesting condition to impose is this: d bar alpha dot on phi is equal to 0. Now, the question you might ask me is, why don't you impose more? Why don't you impose the conditions d bar alpha dot on phi is equal to 0 and d alpha on phi? What is the answer to that? Is it the first question? Is this supersymmetric? If I impose both conditions? Yes.
D comma.
Yes, it's supersymmetric. Yes.
Sorry, what is the d comma d bar commutator?
Excellent. So Shuman's got this fine. D comma d bar commutator maybe will flip a sign. It will be this.
Yeah, it will be non-zero.
It will be non-zero. And so if you impose that both d and d bar are negative field, you'll impose that the derivative is negative field. So you'll impose that it's not a field, it's a number. Okay? And so that's not what we do. We don't want to trivialize the theory by making fields not fields. So the best we can do is impose one of the two, and this by convention we impose d bar alpha dot on phi is equal to 0. Okay. Any field such that d bar alpha dot on phi is equal to 0 is obeys the condition d bar alpha dot on phi is equal to 0 is called a chiral superfield. As in the one-dimensional case, quantum mechanical case, you remember chiral superfields could never be real, because our reality condition for superfields was given by interchanging theta and theta bar. Complex conjugation involved an interchange. I mean, took theta to theta bar and also interchanged order of anti-commuting variables. This you remember. rule for complex conjugate statements. Okay, and since we put a condition on theta bar, but no analogous condition on theta, clearly if phi was real, we would get a contradiction because we complex conjugated it, we would get the statement B alpha on phi is equal to 0. The condition be not true. So instead, it becomes condition B alpha on phi bar 0. And it's a true condition. And it's all consistent because phi is a complex. Okay. Now, in okay. Now, you remember that we discovered how to solve the condition. B bar on some field was equal to 0. Okay. You remember that what we did was that we invented a new X type quantity. Schematically, it was of the form T plus theta theta bar. Right? And our solution was that something of a d bar on phi was equal to 0 if it was a function of theta and this new X type.
We constructed the invariant.
Yes, a quantity that was annihilated by d. Okay? In a very similar way we proceed here. We construct an object which is sort of like X, but with an additive bilinear thetas that is annihilated by d. Okay? And that quantity is y. Yeah. Y mu is equal to x mu plus I theta sigma mu theta. When I have this theta sigma mu theta bar, I mean the indices are constant. Okay, so this means theta alpha sigma theta dot. Okay. So consider this quantity here. This y mu is equal to x mu plus this bilinear theta, basically like theta theta bar. The generalizing. All we're doing is generalizing everything we did in quantum mechanics, but keeping track, making sure it's all correct. That's basically how we're proceeding. Okay, so the claim is that this quantity is annihilated by delta. Now let's check this. Okay, so what I wanted to check is that minus del by del theta beta dot minus I theta alpha sigma alpha beta dot mu del mu acting on x mu, let's say, plus I theta gamma sigma gamma delta dot theta bar delta dot is equal to 0. Sigma mu. Oh, then we call this theta. Okay, I will check this is 0. Okay, so let's see how that goes.
Del by delta bar.
Del by del theta bar. Thank you. Del by del theta bar. Absolutely correct. Okay, so this is an operator acting on this quantity. Okay, this guy gives 0 when hitting this, but something non-zero when hitting this. And this guy gives 0 when hitting this, but non-zero when hitting this. Okay, so let us check what happens when this guy hits this. That's very clear. This gives a delta mu. Okay, so we get minus I theta alpha sigma alpha beta dot mu. Mu with a delta mu. Right? What about this fellow? Okay. This fellow hitting this guy gives us
Plus sign.
plus sign and a delta beta dot delta dot.
Yes.
Oh, we'll just make this beta dot here.
Yes.
Plus I zeta nu beta dot.
Yes.
The delta mu changes the mu to the
The delta mu nu changes the mu to mu. That's fine.
and zeta and alpha rated
That means so they cancel. Sorry, where is
I am worried about the fact that this was only non-zero when mu was equal to nu,
and
whereas this always looks non-zero. Where is mu?
no, but
Oh, mu was a dummy variable. Thank you.
mu is a dummy
Dummy variable. Thank you. Yeah. So this was. Thank you. Yeah. This was. Thank you. Right. So this was just. So this is equal to 0. Excellent. Excellent. So we verified that this y mu is annihilated by v bar. Therefore, if we take a field phi and write it as the most general function of theta alpha and y mu, then this is the most general chiral superfield. Please.
So there are 16 possible.
Yes.
And this d alpha that would give something to constraint.
It gives two constraints, but two constraints tells us that two thetas are not there. So it cuts down 16 to 4. You see, let's forget about the complication of, suppose this had been just d by d alpha rather than this capital D alpha. Then it would tell us that it's not a function of theta bar 1 and theta bar 2. So not only does it give the theta bar times function of x, it also gives theta bar times theta times function of x. Anything involving theta bar 0. Or it's theta bar theta squared. So it's many conditions. Many conditions when you count scalar functions. Is this clear? Of course, the simplest way to see this is just to say that, well, now there are only two non-commuting variables.
sorry, I remember that. Is it a simplification you want to make, or is it a choice you can make in the problem and there is a spec?
Well, what we want to do is to make the smallest superfield
Oh, okay.
that will continue to be supersymmetry.
You are doing it coherently.
Of course, it has to be covariant. That's what Lorentz varies, as well as have a supersymmetry.
Yeah.
Because otherwise you won't make a supersymmetry.
Yeah.
Okay? Typically, if you didn't make this, what you will get is not one irreducible multiplication, but many different multiples. You want to do with deal with the irreducible. It's the smallest thing you do. Right? Okay. So the field we have to deal, the most general field is phi of theta alpha and y mu. And you remember that now if we want to count variables, clearly there are 4 functions. Because there are 2 theta alphas, each of which is there or not there. Okay. So if we take the most general chiral superfield phi and we expand it, let me use its notation. We will get is equal to a of y, okay, plus square root 2, this is for fun. So other formulas I suppose become better. Theta psi of y plus theta f of y. Now there's some irritating possibilities when we propose theta. We define a convention somewhere. You know, theta is of course contracted with epsilon. But the question is, which epsilon? Is it plus 1 or minus? You know, that is always. And there is a convention here which he always uses again. Yeah. Sorry, just one minute. Appendix 8, thank you. Yeah, perfect. Okay. Yeah. Let me write down all conventions here once and for all. Okay. Psi alpha, when we raise an index, this is how we always do it. It's epsilon alpha beta psi beta.
That might be one.
Okay. That might be out of frame. Okay.
That line is.
I think this was my line.
Yeah.
I can see it. Perfect. So thank you. Psi, yeah. Alpha, epsilon alpha beta psi beta. This is always a convention for raising and lowering. And the convention for contracting here. Whenever I write psi chi, what this means is equal to psi alpha chi beta, psi alpha chi alpha, okay, which is the same as minus psi alpha chi alpha. Can you see that the first and the second leg with each other? Yes. Okay, because at some you have to get two epsilons, which will square to minus 1. In between these, there are two epsilons. Let's just check that. So psi alpha here, let's use this. Okay. So let's psi alpha is equal to epsilon alpha beta psi beta. And let's write this as psi beta is equal to epsilon beta alpha psi alpha. And now we need to define what these two things. Okay, so for these to be consistent, okay, it must be that if I plug this into this, I get back this quantity. So it must be that epsilon alpha beta prime, epsilon beta prime nu is equal to delta alpha nu. That is the consistency of these equations. Okay, which tells us that this is the inverse matrix of this. Okay, but that tells us that this is not exactly this. Right, because if I take 0, 1, minus 1, 0, and I want multiply by 0, 1, minus 1, 0, I will get minus identity. Right, because this is I times, it's related to I times sigma 2. So this matrix epsilon doesn't square to identity, it squares to minus identity. Okay, so as a tensor, if epsilon, let's say 1, 2 is equal to 1 and epsilon 2, 1 is equal to minus 1, suppose we use that convention, then it means that epsilon 1, 2 is equal to minus 1 and epsilon 2, 1 is equal to 1. As tensors, they're minus of each other. Okay, the guy with lower and the guy with the upper are minus 0. All these are irritating things about 4-dimensional trigonometrics. which hopefully will not bother us very much. Okay, but just to expose it once. Okay, so this is what I meant when I said theta theta. It means, sorry, which one second? It means theta alpha on the first, theta alpha on the second. Yes, please.
So epsilon is I sigma 2 and like extend this sigma as like one index of the left and one index of the right. Then why does the epsilon have two things at the same time?
This is the same question that that we asked the guy from IIT Kanpur. You see, sigma mu alpha beta dot with both indices down, this transforms like a vector. Okay. On the other hand, if we take sigma 2, okay, either this or alpha dot beta dot, this transforms like a scalar. This is the question. We address this question for the C matrix. You remember what the question was then? The question was that the C matrix was a product of gamma matrices, of alpha gamma matrices. And the question was, when the gamma matrices transform like vectors, okay, the gamma matrices transform like vectors, why isn't the C matrix transformed like a half-rank tensor rather than a scalar? And the idea was it was depending on which density this is going up and down, or both down. Okay, so in this case, the sigma 2 matrix with both indices put down transforms like one component of a vector, which means that it has one index dotted, one dotted, the other index. Okay, but however, the sigma matrix with both indices up, these indices can be chosen to be either alphas or betas, transforms like an SUV scale. This is familiar, right? It's like it does a transformation. We even showed this as something. Okay, so the same matrix is just the same. It's the same matrix components, but it's a different function. Clear? Yeah, it should be thought of like that kind of object. It's raising the volume. It's the C matrix. Remember, C matrix had raising the volume. It's that thing. Is this good? Okay, excellent.
So, sorry, the fundamental fields are the lower ones.
Fundamental meaning what?
When you write psi beta or psi alpha.
Yeah, when I write psi beta or psi alpha, I will always choose lower. Yes, but we will often write contractions.
Yes.
And then when we write contractions, this is the first index upper, second index.
Yes.
Okay, so when I write theta theta here means theta alpha here, theta alpha. Okay, excellent. So let us keep going. So we have this expansion here. This. Where 3 fields in 5? I'm sorry. Thank you. Plus square root 2 theta bar psi bar y plus theta theta theta. That's no theta. No, sorry. This is right. Because this is contraction of 2 fields.
What theta psi is a contraction.
It's a contraction of 2 fields. There's 2 components.
Sizes.
Yes. Yeah. No, this is just right. Okay. Excellent. Now the next thing we can do is to take this and rewrite this guidance as a function of theta bar x. Namely, just to open out the Taylor expansion in a Taylor expand these fields in theta bar. Right? We never need to Taylor expand more than second order. Because there are only 2 thetas and only 2 theta bars. So theta bar cube is 0. Okay. And then for okay. So I'm just writing out the answer. And then we look at the answer and we tell me to Okay. So when we do this Taylor expansion, we get A of X. This, by the way, was the point of working out that quantum mechanics example in so much detail, where there we did every component of the energy, so that you believe it or not. Now I will try sometimes just to skip algebra, just so that we believe. Okay. So we'll get AX plus square root 2 theta psi. Okay, let's write it. AX plus I theta sigma mu theta var del mu A plus 1/4 theta 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 bar del squared A. So this was what came from expanding Y. When, as we said, we could have at most second order and Taylor expansion, because we could have either theta theta bar term or the theta theta bar square, both terms are there. Okay. Now here, to what order can we go? First order. Because if we go to second order, we get 3 thetas. We have very similar considerations of looking at quantum mechanics. Okay, so plus square root 2, of course, one term is just theta psi, plus and minus I by square root 2, theta theta, theta theta del mu psi, sigma mu theta bar. And for this guy, to what order can we expand? 0. Plus theta theta. Okay, so phi of X, the most general chiral superfield, admits this extension. Okay, so it's defined by the 4 functions A, F, and the 2 psi's. And in terms of these 4 functions, we get this expansion. Okay.
So, sorry, when 4 things are written, how to read this? The first 2 things are contracted and the second.
You see, you can never have contractions between theta and theta. Because theta belongs to one SU2 and theta bar belongs to another SU2.
Yes.
So it's always theta theta are contracted with each other. So where was this like? These 2 are contracted?
Yes.
And these 2 are contracted. Always upper, lower, upper, lower.
Yes. And here psi is contracted with theta bar.
Here psi theta, here theta theta,
And this is 3 object.
and
Like psi alpha sigma and
yeah, these indices are contracted. Psi alpha, sigma alpha, beta dot, beta alpha.
These are the mixed.
Right.
Some sigma identities to get the difference.
Did we use the sigma identities? I don't know. You want to try it? Probably we use some. How are you asking where did the sigmas go? Yeah, we're probably using some sort of completeness. Okay. If you're uncomfortable about it, we can try it.
No, but del square is just a Taylor one.
No, the question is why don't we get 2 sigmas?
2 sigma, we know that 2 sigma is, this epsilon and delta, this 2 sigma is.
It's some sort of completeness.
Yes. It's sum over delta and epsilon.
Yeah. Are you uncomfortable? Would you like to do it or would you just like to try this? Right. Yeah. Okay, let's move on. This is simple. Okay, excellent. Fine. So now, if you remember when we were studying quantum mechanics, how did we use chiral? The really important thing about chiral superfields was the following. The really important thing about chiral superfields was that we could build a Lagrangian out of them by integrating over half of superspace. The 2 theta of any chiral superfield. Any chiral superfield xi, which is a chiral superfield. But you know, the way we're going to make it is by making it a function of other chiral superfields. Okay, so I'll write it here as f of phi. Let's call it W of phi is supersymmetry. Okay. Can somebody remind me of the argument for this? Why is this a supersymmetric Lagrangian? Is it totally? Because excellent. Yeah, because excellent. So the question we have to ask is when we take this and we act on it with the supersymmetry charges. No. That it would be d2 theta bar was not that. d2 theta bar will be correct for the kinetic function of phi phi bar. But for the chiral part, for the superpotential, was d2 theta. Okay, that was the point of these chiral superfields, that you can do it over integration over arms. Okay, so now Sunil's point was the following. His point is to check whether this is supersymmetric or not. All we have to do is to act on the Lagrangian, act on the action with the supersymmetry generators, and see if we get the same Lagrangian as a transformation. No. Okay, so let's act with the act on the Lagrangian with these supersymmetry generators. And supersymmetry generators were made up of two pieces. Okay, the first piece was del by del fermionic quadrant, and the second piece was a total derivative in space. The second piece will never contribute because it will always, this whole thing is some chiral superfield. So it's transformation on the supersymmetry. So we can just call this whole, forget that it's function of phi. This is just W some chiral superfield. And then its transformation from second piece will be total derivative of the W. So the only possible place where we can get contributions from is from the first piece. This is clear? Okay. Now so the first piece is different depending on whether we're doing Q or Q bar. Let's look at when we're doing Q. When we're doing Q, the first piece was a del by del theta, but d2 theta is a del by del theta. And so that obviously gives 0 because you get 2 del by del theta, the del by del theta space. Okay. Now what about the second piece? The second piece looks like it doesn't work. This is where Kanu's remark comes in. If we didn't have chiral superfields, this Lagrangian would not be supersymmetric. So it would indeed be left invariant by the action of Q, but not by the action of Q bar. Because we would get del by del theta bar term, and that would not be 0. However, this field is chiral. So it means that D bar on this field, W is equal to 0. But D bar of W is equal to 0. Now D bar is equal to Q bar plus some 2 times del mu. You know what I mean? The difference between D bar and Q bar with the appropriate sign is purely in the second term. And that second term is a total term. Del mu. So for chiral superfields, when you're integrating the chiral superfield, this Lagrangian here was invariant up to this total. So the action was invariant under the transformation of all superfields. Now all supercharges, Q as well as Q. Is this clear? Excellent. So one way of writing down the supersymmetric Lagrangian in terms of these chiral superfields was d2 theta W phi. This is what we call, if you remember, superpotential. This is superpotential about it. Okay. In order for this to be real, you would also have to have plus d2 theta bar W bar phi bar. Because we always want to deal with real actions. Okay, And then in addition, we dealt with this scalar potential. The scalar potential term was simpler thing, d2 theta bar times k of phi bar. Some function of phi bar. We didn't completely complete that discussion, but this k was related to something nice in geometry. We'll come back to that. Okay, that this is supersymmetric, there's nothing to say. Because in the integration over all four thetas. So if we act with any of the q's, the first term is obviously 0. And the second term is also obviously 0 because it's a total. Okay, so this was a less special term. The whole point of superspace is that we integrate over all of superspace. Obviously, with supersymmetry. Okay? But sometimes you can get away by integrating over half superspace. Okay. So when we study four-dimensional field theories, we will study theory. We are going to be studying theories with both gauge fields as well as time. Okay. Macro-Lagrangian in the UV theory, in the ultraviolet, will simply be given by some choice of the superpotential, if at all, some simple choice of the superpotential, plus standard kinetic term, which will be phi bar. If you remember from our discussion of quantum mechanics, this standard kinetic term, oh, by the way, you remember this was kinetic. You remember that it didn't look like it. But you remember that when we expanded, because phi was a function not of x, but of y. Y has, when we expand this y, we get derivatives. Okay? And you need to do such an expansion in order to saturate all the d2 theta bar integrals, because yes. Right. So there are terms in which you do this expansion, you saturate the integral, and those terms will give you the kinetic term. And if you remember when we discussed quantum mechanics, we looked at exactly this example, and we got the standard kinetic. Del V phi squared. Here we will get del mu phi del mu phi.
In this, del square.
Say that again.
Del square.
Del square. Thank you. Del square. Yeah. This would be right. This would be del mu a del mu v. We get it derivatives. Okay. So this was the kinetic term. This function here, this k, controlled what the metric dependence in field space was. Not in, now always, we have to distinguish between metric in field space and metric in the space where the field theory is. Always working with field theory and flat in Gaussian manifold, but in field space there might be a metric, which is contained in the kinetic term. Fields, here we're working with a flat metric even in field space. Okay. We choose to work with this flat guy in field space because in the UV we want to deal with the renormalizability. So we want to deal with something that's dimension 4. Anything that was at more fields, more A's here would be dimension 6 and higher. This here arises the quantum effective action again. But in the UV we want to start with something nice. Okay. Similarly here we will deal with very simple superpotentials, as you will see, limited in the UV, limited by the requirement that we want the derivative when the factoring on. Okay? All good? Fine. So our matter theory will be described by the matter sectors of the theory will be described by Lagrangians of this. Any questions or comments about this before we get to study the gate sector?
Is there an example where this boundary plays on your saturating?
In integrating by parts.
No, in the supersymmetry
Derivation. In supersymmetry derivation. Presumably, if you study the theory on manifold, then you will have to choose your boundary conditions on the boundary of that. to make sure that this still works. And you could imagine that for example. Yeah. What?
Normal here does this boundary from creating.
Yeah, normal Chiral boundary term. For instance, the boundary term that you get when you derive the equations of motion. Yeah. Yes, it plays a role. You know, these boundary terms you get when you derive the equation of motion are closely related to symplectic form. Let's take an aside and understand this. Let's take a theory of just non-relativistic quantum mechanics. Okay, so suppose our non-relativistic quantum mechanics theory was Gij xi dot xj dot m by 2. Then there could be some potential. Now, let us take the variation of this action with respect to one of the x's. Okay. When we compute the equation of motion, we need to integrate by parts because we don't want a dx dot delta x dot. We want all our delta x's to be out. Okay. So when we get so what is the term that we need to integrate by parts? Well, the factor of 2 cancels. We get this mgij x delta xi dot xj dot. This was the term we had. Then we integrate by parts. So we get d by dt of we get a d by dt of we take this delta outside the whole thing. So xi xj dot and then minus whatever we get, that gives us the equation. Okay, so this with the Gij was a boundary term.
So delta xi.
What?
Delta xi.
Delta x. Delta x. Yes. Okay. Now notice what the coefficient of this delta xi is. It is Gij xj dot. But Gij xj dot is simply the momentum conjugate to xi. Okay. So the first thing about these boundary terms is this, that when you look at you look at this boundary term, and you look at the coefficient of the delta xi range, you get the momentum conjugate to xi. In fact, this is something you know. It follows from Hamilton. You know, we normally look at the principle of least action with fixed x at the beginning and the end. That's why this delta x, this term here, vanishes because delta x at the two ends is 0. But suppose you allow yourself to, in doing your variation, also vary x at the moment. Then the action is no longer invariant. It changes. But its change is given by something extremely simple. The variation, the coefficient behind that change is simply the momentum conjugate to that. That's what Hamilton Jacobian is. And we're seeing that there. So this variation kind of term then closely connects with the symplectic structure of the thing. Okay? There is another connection which has to do with the boundary term, which is nearer to the question you actually asked. I deviated into this because I find it interesting. But the question you actually asked was this: if you want to really derive the equations of motion for everywhere. Yes.
But I think using the Suji there.
Oh, using the supersymmetry. So you want to study supergravity.
Yeah. Okay. Then like these boundary terms that we know that there be in W and all that. Does it any?
I will have to think about that. I think you would need a supersymmetrization. You know, your action in the bulk will have this. Your boundary term will also have this. The given talking term, which is a boundary term you need in any way in GR, will also get some appropriate supersymmetries. if you study Sunil. Right? I mean, I think it will be as right. So in order to ensure that Sunil's question is not an issue. I haven't thought about it. That's all. Okay, excellent. So let's get back. So we're very happy with our matter set. Any other questions about it? We understand how to write a Lagrangian form. I now want to tell you how to write a Lagrangian for gauge fields. Okay, but first, any questions about this?
Here, these A fields and psi fields are complex previously.
Yes, A and psi are both complex. Okay. So
there are 4 complex fields.
yes. Now there is actually one more thing I want to tell you. Okay, please. This is free. No, it's not necessarily free. That W of 5 could get unique term.
But this is the only way to create integrals.
This is the only way to create renormalizability. If you give up this criteria of renormalizability, both the superpotential as well as the Chiral potential can be any function. And that is far from free. For instance, you're looking at effectively. The Chiral potential and superpotential can be arbitrarily complicated.
No, I'm saying W of I, writing W of I as a function of I is the only way to create.
Well, the other way is to make a more complicated Chiral potential. Instead of just phi,
yes.
you choose some K of this.
Yes.
Okay. Right. And of course, if we give up this thing of renormalizability, we are also free to add mu. We can add a function not just of phi and phi 1, but in giving out derivatives, spatial derivatives of phi and phi. Remember, spatial derivatives also repeat. Okay, so if you're going to allow yourselves not to have arbitrarily normalized, arbitrary high dimension operators, you can write many things. I'm just looking at the low dimension operators. Please.
Simply by itself, make sure the theory is potential.
No, of course. That's what I was saying. For instance, you can choose an arbitrary Chiral potential.
If it doesn't do anything to the ultraviolet instead of
Yeah, I mean, Supersymmetry does something good to ultraviolet divergences, that's true. But if you start with something that just has dimension full time.
This is the marginal operators. There's 4 dimensions, the 2 operators, those kind of interactions. Then does Suzy help with renormalization?
Suzy helps make things more renormalizable. But any good one supersymmetry is not in itself enough to cure everything. Okay. In fact, any good for in some cases very good too are enough. And that's why any good for angle theory is a problem. Beta function. Beta function is associated divergence. Okay. Whereas any good for theories, you do have non-zero with beta. Okay, so we will get to this. We will study some non-renormalization theorems as we. It's a good question. Okay, let us proceed. All good? So there's one more thing I should have. I was being lazy. One more thing I should have done was to open out this action. Let me do it. We've done this in the case of quantum physics. Okay, I'll just give you the example. Okay. So if I take this plus integral v to theta bar phi 1. Okay, then what does this Lagrangian become? Now this is just mimicking our algebra that we did so painstakingly in the quantum mechanics. For every I right, every minus right. Okay, here I'm just going to trust myself. Okay. So we this is what the Lagrangian. It becomes inter v for x I what a terrible paper. Okay, I'm going to write it in his way so I don't get anything wrong. This is del slash in a very strange way of writing.
Sorry, this is slash. Sigma mu is also there.
Sigma mu is here. So that's what we call del slash.
Yes.
I'm saying this is the usual Dirac Lagrangian.
Yeah.
It's just written in a very funny way.
Left del slash.
Yeah. Now he's looking at the Lagrangian that you get with I. So let's say there are many kinds. Okay, and this thing is a superpotentials function of all of them. Okay, so you get this plus AI star box del square. AI plus F star I Fi. Okay. Plus, oh my God. Okay, now I have to. He restricts to the special case of M I Phi j plus G I j k Phi j phi. So restricting to renormalizable superfields. That's complex actually. Okay, we could work this out in general for W, but he's restricting to the special case of renormalizable superpotential, which anyway is what we will have. So fine, plus Mij AIFI minus half psi I psi j plus what?
AIFJ, my dear.
Aij. Thank you. Plus Gij AIAJ FK minus psi I psi j AK plus lambda IFI plus CC. I think this whole line here is plus CC. Oh, it's probably the beta. Sorry. Very good. I'll tell you. It's probably the F. Okay. It's the F term. Let me just treat. Section here by 2 by 3. And he added here of plus lambda I phi I. You know this. So it's allowing a linear, quadratic, and cubic. Yes. Okay. And so in doing this, he gets this expansion here. So far, not integrating out any auxiliaries. Okay. Now notice here, But this is the Dirac action written finally for phi's. This is the kinetic term action written without an integration by parts for scalars. And this is not a kinetic term. It's just an algebraic expression. Moreover, it's quadratic. This tells us f is not a field. We can do the path integral over there. Now, every quadratic term, we can always do the path. But usually, quadratic terms are quadratic terms involving kinetics. So when you do the path integral, what you get is something ideal. It's not a good idea really to do the path integral quadratic terms. Because you get some non-localness. Okay, but here we can just exactly do the path integral. Because there are no kinetic terms, it's local. All that does is replace x by its equation of motion. Right? It's completing the square. Okay. So now when we replace f by the equations of motion, what will we get? Okay. So let's look at the equation of motion. Let's say the equation of motion for f star. We get fi. Since we don't know the f's here, let's do the equation of motion for f. We get fi star, okay, plus mij ai plus gij aj. Now I did it for, sorry. I want to keep I as the index that so this is I, so jji, and here was kji plus lambda I is equal to 0. Okay, so you see what this was. Though we've written out in components, you see what it is. It's the derivative of the superpotential. Okay, with respect to phi I. And then evaluated at A. Okay, so our equation was that fi star was equal to del W by del, let's say call it AI, maybe with a minus. Okay, so on shell, this F field, this F superfield, is the derivative of the superpotentials with respect to the chiral multiple. And then we're supposed to plug this back in. Now, when you plug this back in, do you see that what we're going to get is, well, two things. From here, we will get this times its complex contribution. And we get that with a plus sign. From here, we will get the same thing. You see, what we have here is like this derivative.
Is it AI or AI?
What?
Is it del W, del AI or del Fi?
It's with respect to phi, but phi is then evaluated at AI. If you want, this is phi. But at phi I equals A. Now you take the superpotential is function of the chiral field. You differentiate with respect to the chiral field, but then evaluate that at theta equals 0. At theta equals 0, the chiral field is AI.
I was thinking about this quadratic term, kinetic term for AI, and if you write it up to the derivative, like you can write it as AI del square A star, right?
Well, the kinetic term has nothing to do with this. We're looking at the potential terms. So the terms involving F. Okay. That only comes from here. Okay. Right? So the fact that we took the derivative with respect to we took the derivative with respect to F, the thing was linear here in F. So you see, what we said here was that this thing was del W by del phi I times Fi.
You are calling this
This quantity here was del W by del phi I times that time. And that's, if we derived it out of there, that's how we get it.
Yeah.
So this is unnecessarily explicit. So it's del W by del phi I times Fi. So now when we put Fi is equal to this guy, we may get minus del W, Fi in the other guy, we would have del W bar by del phi I bar times Fi bar. So when we put F star, which is F bar, is equal to minus del W by del phi I, we get del W bar by del phi I bar times del W by del phi I, but with a minus sign. But there are two such terms, because that's when you substitute F bar and when you substitute F, both of them come with a minus sign. The term there came with a plus sign. So overall we get a minus, which is what we want, because we want to get T minus P. Potential coupling should come with a minus sign. Okay, so eliminating this F using its equation of motion gives us an effective potential. This is the point I want to make, which was del W by del phi I mod square. V is equal to this. Okay, and then in this very irritating way, when you expand it down throughout, you will get it very explicit. Is this clear? So the point I wanted to make here was this F here was an infinity. You can integrate it out quadratically exactly without making any approximations. And when you do that, you get a potential. When this potential was V is equal to del W by del phi I squared. Actually, this formula for the potential is so simple only because we chose the metric, the flat metric in Chiral. Otherwise, we would get, these two things have an index in field space. And those indices are contracted by the metric in field space. The metric that follows from the given. So in general, we will get that structure and fine. Okay? But this is the point I want. With the flat metric, the Lagrangian is very simple. It has the standard kinetic term for the fermions, standard kinetic term for the bosons, and just a particular potential which was this. Is this clear?
This potential is evaluated at AI.
Evaluated at AI. So I differentiate and then set theta equals. So if I set theta equals 0, am I?
There will be extra inside
Oh, absolutely right. Sorry, you're right. There's this potential plus there are the extra interaction terms from the fermions. Thank you. In addition, there are the terms which are psi I, psi j times AK. Now, the psi I, psi j times AK can also be written in terms of the superpotential. They're essentially second derivative of the superpotential, contracted with psi I and psi j. Okay, and because it's second derivative of the superpotential, second derivative of the superpotential now psi I, the second derivative of the superpotential contracted with psi and psi j should give, there should be a mass here. This term is the mass term for the fermions, and in addition, when there is a cubic term, there is an interaction. Thank you. So in addition to this potential, there is also interaction between the fermions by themselves because of that. So the general structure is psi I, psi j, second derivative of superpotential, del Wi, del Wj. And the derivative is always evaluated at phi equals 0. Is this clear? This is the structure of kinetic terms in what I mentioned. I know that for many of you this is boring. Right? I mean, many of you know this stuff, I'm sure. But just for complete. How many of you are familiar with this? 1, 2, 3. Is it everyone? No. Okay. Because everyone we could do. Okay. Then that's it.
So, you said when you integrate out the quadratic term, you get non-local term for
usually, if you have a non-zero kinetic, yes.
that only happens with derivative term.
Yes. If you have a propagating field, which happens to be quadratic, but interacting quadratic in itself, but interacting with other things. So for instance, suppose you had in standard model you have fermions interacting with heats. If you integrated out the fermions, you've got an effective action to the heats. It would be horribly long.
There are derivatives of the
Infinite number of terms.
Yes.
Right? Because you see, when you have schematically what you do, you have a term that where you have alpha alpha plus alpha b. Now, when you e to the power minus, when you integrate this out, this comes in the denominator. So let's say alpha b with some, okay, whatever. So you get b schematically 1 over this thing. Now, this thing has derivatives, you have 1 over something with derivatives. And that is an infinite number of derivatives. Right? It's not local action. Right? There's often situations in physics where you have an interesting Lagrangian in which the Lagrangian is totally, in general, is an interacting. But if you focus on one field, it's quadratic. So you might wonder, why don't I just integrate out that one field and simplify my life? And you can do that. But the price you pay is that for what remains, you've got highly non-local. Okay, let's look at I don't know. You see the interacting with quarks. Quarks are quadratic. You can integrate them out at the expense of using a horribly non-local action. So again, bosons, not generally useless.
that doesn't lead to any
Sometimes. About 10 years ago, we solved matter Simon's theory doing that. TIFR solved two-dimensional QCD. Sometimes it's doing. What happened there? You see, what happened both TIFR's case and our case is that we were in some large N case situation, so we got some non-local theory, and because of that, in at large N, both TIFR and we got integrity. The non-locality can be integrity. It's interturning local things and differential equations, non-local things. In the case of those those integral equations are different. In our case, we somehow miraculously managed to solve them. Okay, so you get something non-local, you can deal with it. You're in good shape. There's nothing wrong with it.
These are exceptions.
These are exceptions. And it was very common to use Nagi. When you are path integral of these non-local things, it will be this. Effectively, you do classical physics over these non-local things. So just we can solving a classical integral equation. Sometimes you get better. Sometimes it's useful. I mean, in my experience in physics, you should never have ideology. You should never say this you cannot do, this you do. Because you generally know. Often what the things that people tell you should never do, you do it unless profit. In the right situation. I mean, people tell you not to do it because 98% of the times it's a useless thing to do. And then people have generalized in their mind to it will never work. But there is the 2% that it will. You should just be open. Open mind. Okay. Great. So, I think that's all I wanted to say about the matter. Are we all good? Okay, excellent.
Degree of freedom of
Sorry, say again.
degree of freedom.
Good. So, how many degrees of freedom will there be? Good. So, in the counting, that we have 1 degree of freedom for a real scalar field. You're right that every phi is polynomials. Let's do that. What is the number of degrees of freedom in phis? In each phi? In each scalar, each A. 2. Because it's complex. Now, what about so that's scalars are always easy. Now let's look at the fermions. So the fermions, how many fields do we have? How many real fields do we have? 4, because we have 2 chiral quantity. Exactly. So we have 2, we have 2 psi bars, and so we've got 4. Okay. But these two sides and two sidebars, these four fields, okay, first order equations. And so the degree of freedom is 2. So total number of degrees of freedom is 2 and bosons 2. All good? Okay, excellent. Fine. Now we want to deal with these gauge bosons. So what do we do? In order to deal with gauge bosons, okay, in order to deal with gauge bosons, we do the following. We introduce a real superfield field. It's real, okay, but it has no chirality. Okay. So it's a real field with no chirality. So it's one of these horrible things. Okay. So this is some real field. And I could write down the expansion for you, but there's nothing. Every term that can be of does. There's a theta term, there's a theta bar term, there's a theta square theta term, and so on. Okay. When we need it, I will write it down. The only thing, the only place I want is when you write down the term which is theta alpha sigma mu theta bar alpha dot. Okay, so the term that is theta alpha theta bar alpha. Okay, this term, how many terms are there in that? Well, there are 2 thetas, 2 theta bars over 4. We can, we can convert that to a vector. So we do that, and this term has a term which is v mu here. This v mu will be the vector which will become the gauge function. So it's a long expansion, and maybe I'll also introduce the thing that will be the kg.
So sorry, the indices, the sigma mu indices are getting contracted with what? This theta,
Sigma mu, v mu.
No, it's
Alpha.
Okay.
Right. I will also introduce, there is also a term which is plus theta bar lambda bar. It's I minus I theta bar theta lambda. So this order we introduce a fermionic field which are also thermodynamic physical. And this field is the gauge. Then there are many other fields that vary up various other orders. Gaugino is the super partner of the gauge. Multiplet involving the gauge. Gauge boson comes with the fermion. That field is called a gauge.
It's like psi and
just like psi. Exactly. Okay. I will write out this expansion of the parts of it that are needed as we need them.
What are these dots?
Dots means you see. So for instance, let me write down the first feature. There's some c of x. This is a term with no thetas. Plus there is I theta chi plus minus. Okay, let me just write it out itself. I'm just writing out the whole thing. V is equal to c of x plus I theta chi minus I theta bar chi bar plus I by 2 theta m plus I n. Okay, minus I by 2 theta bar m minus I n. Okay. Minus theta sigma mu theta bar v mu plus I theta bar lambda bar plus I by 2 sigma mu del mu chi minus I theta bar theta lambda plus I by 2 sigma mu del mu chi bar plus half theta bar into B plus R del squared C. Okay, what is the point of this expansion? Point of this expansion is that if we want to expand the whole thing, we need 16 independent. Okay, how you do it those 16 independent fields is a little bit up to you. Western diagram has done it in a way that will help. Let's count the fields. Okay, there is C, that's 1, M, 2, N, 3, D, 4, and then V mu, which is 4 more. So that's it. 8 goes on. Okay. Then there's chi bar, lambda, and lambda bar. 8 for me.
Theta bar.
This one? Theta bar.
Minus I.
This is theta bar. Thank you. Okay. So we expanded it down to 16 different fields. And we've done it in a way that's convenient for us. Okay, you could ask, why did I just call this lambda bar? Why did I put this extra term here? Well, it's going to be later on convenient. All good?
C, M, and E, these all are different.
Different things. Each one of these at the moment is an independent scalar. Independent real scalar.
The superpotentials, this chi.
What is the super? Most of these will turn out to be either pure gauge or will turn out to be auxiliary fields. The physical fields will be just mu and v, lambda and lambda. We'll see this. Okay. At the moment, I've just written down the most general expansion of a real superfield. I've done nothing. Okay. Now, let us suppose that we are going to work with an abelian field. Just for a moment. Okay, we generalize non-abelian fields in into maybe. So if we're going to work with an abelian field, we want this field to represent a gauge boson. And the really important thing about the gauge boson is gauge invariance. Okay? So we want this field to have gauge invariance, but in a supersymmetry. Okay? So how are we going to make this field gauge invariant but in a supersymmetry? That is a very interesting idea. Suppose we demand that this field, that the gauge invariance acts on this field by V goes to V plus phi star, where phi is any chiral solution. Okay. What was the point? Remember, chiral superfields are expansions in theta and y. Okay. So because we have these expansions in theta and y, a lot of these terms can be eliminated. But what's interesting is this, that the terms involving theta and theta bar are fixed in terms of the terms of theta and y. And in particular, the terms of theta and theta bar necessarily come with a derivation. Right? So this gauge transformation for V is going to translate into the usual gauge invariance, usual abelian gauge invariance. Okay, let us see that. Okay, so let's take phi and write it in its in the form that we solved for. So phi was equal to a plus square root 2 theta psi plus theta theta. Sorry, that's right. A plus I theta sigma theta bar sigma mu a plus 1 by 4 theta 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 bar del squared a, okay, plus a of plus square root 2 theta psi minus I by square root 2 theta theta del mu psi sigma mu theta bar plus theta theta f. Okay, and psi bar is a complex. We take this and we plug it into this expansion. Okay, I want you to focus on the terms that are theta theta. Okay, so we look at the terms that are theta theta bar, we get this term from here. Okay, there will be a similar term from phi star where this will be a star. Okay, so that will ensure that V mu goes to V mu plus del mu of something real.
Yes.
Okay, which is exactly the gauge variance that an abelian U1 an abelian gauge field has. Is this clear? Okay, so you see that if we decide that we're going to identify this guy as our gauge field, if we take the whole superfield that at this example, then this nice supersymmetric gauge transformation implements the gauge transformation of the vector field. Okay, now
Sorry, what are these chi fields?
what are these chi fields? We will see. We will see as we go. The only physical fields will be lambda,
Oh, that.
lambda bar, and B. Everything else will be unphysical. Okay. So now, when we are dealing with the gauge theories, it is often useful to set a gauge.
Gauge with the constant.
Gauge condition. Okay. And okay. What we can do in this thing is to set a gauge in which C, chi, M, and N are all equal to 0. First, of course, we'll check in a minute that we can actually set that. But first, why is this reasonable? What? No, it will move us out. We're fixing that gauge condition. But a gauge fixing is precisely something that stops you from having that gauge variance.
Every time you want to come back to the
Right? What we're going to do is at least partially completely fix gauge. Okay? Yeah. Now,
we have to choose case I and F record, which makes this.
this thing. So you see, look, suppose we have this phi and phi star. C shifts by A plus A star. Yes. Okay, so we choose the real part of A to be minus that of C. We can set the stage. Okay, next, what about chi? How does chi transform? Where is my
Chi is
yes? Chi transforms with the psi.
yes.
Because this theta here, we take this and we take the term that has one theta, which was this. Okay, so we choose psi to cancel chi. Okay, so we've chosen A, we can chosen chi. What about M? Yeah. Theta theta is F and theta bar equals F bar. Okay, so we can choose F and F bar to cancel both M plus ion and M minus ion. The net result of this is the following.
Why can't we do the simple chi bar?
What?
Why can't we do the simple chi bar and D?
Why can't well, we've already used up our gauge conditions. Right? So we had, what did we have in our hands? We had A, psi,
And then
and F.
yes.
The distant psi bar and A star.
We've chosen psi bar as well. Right? Because we've chosen that we've killed chi, we've also killed chi. I should have. Right? We've used up all our gauge tree derivatives.
There are
Yeah, sorry.
There are 8 functions in phi that are
There are 8 functions in phi,
choosing 8 of them.
and we are choosing 8 of them to be and it looks like 7.
C is 2.
C is 2. Why C? Ah,
D. D. There is a D.
D. That we haven't set that to 0. No, you know what we've done is we've chosen 7. There will be one gauge tree, which will be the usual gauge. We're not fixing gauge completely. We're fixing gauge so that what remains is the usual gauge. Okay. So now, when we've done this, everything on the first line of this expansion is going to be zero. This means all the constant terms have been set to 0. And the theta bar terms. The only terms that's quadratic in theta that has not been set to 0 is theta bar. And in addition, there are cubic and quartic terms that have not been set to 0. Moreover, since we've made this choice of gauge, these guys have all gone. And everything involving chi and C here has gone. Okay, so the expansion that remains is very simple. It's theta bar b plus theta square theta bar lambda bar plus theta bar square theta lambda plus theta square theta bar square d. That's what's left. Okay, so you see that this expansion is now about as simple as that for calculus in Superfield. There's a bosonic field. There are fermionic fields, and these will be auxiliary. So playing the same role as A for the calculus. Okay. Now notice that in this choice of gauge, V cube is equal to 0. V cube by any higher cube equals 0. Obvious, because every term has a lot of thetas. The smallest number of thetas is here. This guy square is non-zero. But any term, if you cube it, has at least 3 thetas or 3 thetas. Okay, so in this choice of gauge, V and V squared are the only fields you can create out of V. Not do anything non-linear at V. Is this clear? So this was the advantage of choosing a gauge where the field starts with high powers of theta. It means you can't do too much of this field. Right? Okay, excellent. So we have not yet, so we will switch. Okay. Now there is a very important superfield we build out of this field. Actually, the superfield is built without necessarily choosing this particular choice of gauge. Okay, and that superfield is this. The choice of gauge is just to show you what the field content is. This by the way is called Western gauge. After Western, and it is a convenient gauge for some purposes. Okay.
There are other
Sorry?
There are other case conditions.
No doubt. No doubt. So often we call it a gauge invariant. Sometimes you work off there. And I'm sure there are other convenient cases. For instance, it brings statutory realization often. Okay. Right. But this is a convenient thing by displaying the physical content of this. Okay. But now, what we're now going to define is some sort of gauge invariant. The analog of F alpha. Okay. And this W alpha is defined as follows. It's defined as -1/4 d bar d alpha. Similarly, we define W bar alpha to be equal to
These ones are
the usual.
this.
No, these are sorry. D bar alpha dot d bar alpha. The derivatives, the supersymmetry derivatives. Yeah. Okay, and W bar is -1/4 d bar alpha dot b.
Alpha dot
Sorry?
alpha dot W bar.
Alpha dot. Thank you. Okay, these guys are the supersymmetric analogs of F alpha, basically. Now, the first thing to notice about W's is that the first thing to notice about W's is that they're gauge invariant. Why are they gauge invariant? Okay, the gauge invariant because phi's obey the condition del bar on phi is equal to 0. Whereas phi bars obey the condition del on phi is equal to 0. But these W's have these and are both of them. So it will annihilate both phi and phi. You have to worry a little bit about order, but it's true. Okay, so this quantity is a gauge invariant. Okay, so if we deal with this quantity, we don't need to worry about choice of gauge. Okay, it's the angle of the field strength. And in fact, if you take the this quantity and the other thing about it is that these quantities are chiral. Okay, W is a chiral field. Even though it's built out of real superfield, it's chiral. Okay, to check that it's chiral, all I have to do is to check that d bar on W is equal to 0. But W here has 2 d bars and d bar square is 0. Remember, d bar has the same algebra as C. C with d bar is not 0. It's a moment. But d bar with d bar is 0. D bar square is 0. Okay? So just because this already comes with 2 d bars, okay? This d bar was basically d bar 1, d bar 2. Any d bar you act on it is 0. Similarly, any d you act on W is 0. Any d bar you act on W is 0, and any d you act on W bar is 0. Okay, so these quantities here are chiral superfields. That's the other problem. Okay, now it's not hard to take this expansion here, plug it into here, and compute the components of W. Right? We have everything we need. We know what D is, we know D bar is. We have to slog away. We do it. Okay. Luckily, Western Zumino have done it for us. We don't have to slog away. Okay. So we find that W alpha is equal to minus I lambda alpha plus delta alpha beta d of y minus I sigma mu alpha beta f mu. And this whole thing comes with a theta beta, where f mu is half. The usual.
Sigma means that
This one? Sigma mu. Okay? And this sigma mu, you multiply as matrices. It has two indices, alpha and beta. Okay? Yeah, this is like a gamma mu. It's like a gamma mu in future.
These are also wide variable. So wide
B, this one?
about the delta.
D is a function of y variable. Yes, D is the function of that y which was x plus. It has to be something like this because we know that it's chiral. So it can only be a function of thetas and y's. And why does it not have a theta? It does, I'm sorry. Plus theta squared. Theta square sigma alpha dot mu del mu of lambda bar alpha dot of y. Every field is a function of y. F mu is also a function of y. So v mu is equal to v mu of y. What? Del mu all it's with respect to the variable of v, and the v is valued on. Everything is a function of y and theta. And then later, if you want, you can ask for what y is in terms of x and theta. Okay, is this clear? I'm sorry for boring nature of this class.
No, but this del mu's,
Yes.
this del mu on v mu.
Yes.
These del mu's are with respect to y.
Yes.
Okay.
With respect to x,
It's
it's like
like
my
it's
doesn't
an argument.
you know the difference between x and y. Yes, it's with respect to y. But anyway, it doesn't matter. Because x mu and y mu differ by a theta bar. So they're differentiating with respect to x and differentiating with respect to y is the same thing. It's just a shift, which is constant as far as x is. Okay, but think about if you want is with respect to the argument. It doesn't matter. Okay, this is the expansion of the superfield that contains the field strength. Notice that this field strength is a fermionic field. This superfield is a fermion. Because it was three derivatives, three fermionic derivatives on a bosonic field. Notice also that it starts with lambda, the Hg, the thing that will turn out to be Hg, and that it has the field strength in it. Okay, and then it has some other stuff. Okay. You know, one last thing I'd like you to notice. The last thing to notice is that Okay, forget it. There's one more small thing which we'll forget. Let's end by writing down what the Lagrangian for U1 gauge field is. It's supersymmetry. The Lagrangian for U1 gauge field is very simple. If you want the Lagrangian that will give you ordinary F mu nu, generalization of F mu nu, simply d2 theta W alpha plus CC. First, is this Lagrangian supersymmetric? Yes, because W is a chiral. Okay. Second, you know what? What is this Lagrangian? Right. What is this Lagrangian? Well, so this W contains lambda, it contains V, contains lambda bar, contains this D. This D is going to play, as we said, the same role as F for a matter field. So it's going to be some sort of auxiliary. So we just take this Lagrangian, we plug in. Okay, we plug in that expansion, evaluate what the Lagrangians we get in components. I'll write it down to you, and this is the last equation that we will write in this class. We get integral d for x into half d squared minus 1/4 f mu nu minus I lambda sigma slash lambda. Extremely simple and beautiful. That's it's sigma. That's sigma mu. Lambda then slash lambda. Between D and F, between the field strength? No, there isn't, because you see this is a purely quadratic image.
We want to collect the term beta square.
Exactly. We want to collect the terms theta square from W. So you will get, when we get, one term will be like this with this.
Yes.
That would be this term. Okay. Another term would be like the theta.
The product of this. The second term.
This with itself, basically.
Yes.
Okay. So there would be a term that is so now I understand your question. You're asking why is there a cross term? But clearly there would be no way to make it work. It'll go to zero if you want that. Because how can you have an F mu nu and a D together quadratically? Right, so when you do that contraction, just impossible. Right? So this is what we get. So what we get is the usual Maxwell Lagrangian plus a kinetic term for an associated scalar. Now we see why we call this the Lagrangian, because the associated scalar, fermion associated field, and we've got an auxiliary field with no kinetic term, this D square. At the moment the D is doing nothing, we will soon see how it can end. How we can actually create a detail. A detail. Okay, but we stop class today. So now, again, I'm sorry about the boring mechanical nature of today's class. We have about half an hour more of boring stuff. I still have to tell you how to deal with non-reading. Done everything for reading. I still have to tell you how we have to work, how we need to work on the interviews. But then we're all set. Then we can start doing this because the mechanics. Okay, questions or comments?
Starting, you say the paper, the reference.
Yeah. For today's class, the references.
Yeah. That is
so for what we're going to be doing after that is I'll write down the the archive number. It's 9509066. It's lectures on supersymmetric gauge theories and electromagnetic duality by interrogator and Simon. They wrote these lectures soon after Simon duality exams. Now we will understand Simon duality in detail.